right? So based on Hooke's law, okay, if we are going to based on Hooke's law, so we know that Hooke's law is stress is equal to U multiplied by epsilon. Okay, so the energy U elastic, okay, is equal. You have to integrate, all right, 0 to strain until U stress, okay, and they multiply by d epsilon. Okay, so that's a formula, okay, that we use, right? So again, coming from here, you know that this over here is your stress strain diagram. Okay, so basically when you integrate the equation of this graph, okay, you get the what? You get the area. Okay, so do we get the same? So all we have to do now, E epsilon y, stress is equal to E multiply epsilon d epsilon. Okay, so once you start integrating, so you have E epsilon squared divided by 2, right? So 0 epsilon y, you substitute epsilon, so you get E epsilon y squared divided by 2. Okay, and we realize that, hey, this is not the same as this as yet. Okay, now is not, it's not the same, but we can uh we can make it the same. So the only thing that is standing down here is on the right hand side you have, or on this equation over here you have Young's modulus. Over here you don't have, so we know that note. Okay, so we know that note that E, right, is equal to stress divided by strain y. Okay, so I have them, both of them y. So you substitute this back into here, right? So this will be, so U elastic can also be equal to stress y over epsilon U multiplied by epsilon U squared and then divide by 2. So you cancel, both of them are the same. Okay, so this and this are the same outcome. So let's do some very simple calculation to look at steel and aluminum. Okay. In terms of energy in the elastic region, unfortunately will be not very useful for manufacturing, but let's do it. Okay, so we have steel. So let's say for steel we know the E is equal to 210 gigapascal, and we know that stress yield is equal to 650, right, megapascal. Okay, so from here we can calculate the U elastic. Okay, so we're going to use the formula. Okay, we're going to use the formula where you have U strength. Okay, so we're going to use this formula over here. Okay, we're going to apply this formula over here, right? You can wait, are we going to apply that formula or something else? Hold on. I don't want to get, so that, okay, I don't want to calculate strain over here. Let's say we don't want to calculate strain. Okay, we don't want to calculate strain, so we know that U elastic, right? We know that U elastic, the formula is equal to stress Y epsilon Y U divided by 2. Okay, we know that formula. So, but I don't want to calculate the strain, so we can also express this as equal to stress Y. So this term over here, right? This term over here, so strain of Y can be equal to what? Stress Y divided by E. Right? So I'm going to replace it by stress Y divided by E, the whole thing divided by 2. So this expression can also be used. Okay, so it's the same thing. Okay, so this we will get 650 times 10 to the power 6 squared divided by twice, divided by 210 times 10 to the power 9. So the energy required, if I can find my calculator. Okay, so the energy 650 power of 6 squared divided by 2 divided by 210 power of 9 is equal to 1.0059. Okay, 1.005.9 or 1.006 times 10 to the power 6 joules per meter cube. The energy required to deform a meter by meter by meter volume of material. So this is the unit for what? For energy. Okay, energy required to induce elastic deformation. So now if we look into aluminum, right? Now we are just looking in the elastic region. Okay, we're not looking in a plastic region. I repeat again, we are just looking at the elastic region. So for this case, we know that the Young's modulus is equal to 70 gigapascal. Okay, for aluminum, and then the Young's modulus, the stress yield is equal to 250 times 10 to the power 6. So from here, you can calculate your yield. Okay, your yield elastic, right? So this will be equal to stress U squared divided by 2E. So this will be equal to 250 times 10 to the power 6 squared twice 70 times 10 to the power 9. So as expected, right? This will be equal to 0.446 times 10 to the power 6 joule per meter cube. So as expected, it's easy to elastically deform aluminum when compared to steel. Okay, now the next region we are going to look at is going to be the plastic region. Right, we will look at the plastic region. Now, plastic region is where it's important for manufacturing engineer. Okay, so for manufacturing, we are more interested in the plastic region than in the elastic region. Okay, so in the plastic region, when the load is removed, okay, when the load is removed, the structure will not return to its original shape or geometry. Okay, will not return to its original shape or geometry. Okay, so now we are going to look in the plastic region. Okay, so we are again, I'm going to focus on the what? Elastic region. Okay, so in the elastic region, okay, we are going to simplify our stress strain curve to make it look like that. Right, so this is point number 1. Right, this is point number 2, and then this is point number 3. And the point number 3 is your ultimate strength. Right, it's ultimate strength. Right, so from here we can express it mathematically in another form. But before I go on, so epsilon PL is the plastic strain. Okay, stress PL is your plastic stress. Right? So this over here, this expression over here, or this line over here, it can be represented with this curve. Okay, with this equation, sorry. Where this expression will be stress PL is equal to A plus by B epsilon PL power of N. Okay. So where A, okay, you can see over there where A is our yield strength of the material. Okay. B is the strain hardening coefficient. Okay. And then N, I'm going to be messy. I'm going to use the other side. Where N okay, where N over here is a strain hardening index. Okay. So this is unitless. Okay. This is in megapascal, or this is in not mega, it can be also be in Pascal. Okay. So this is in Pascal also. Okay. Oh, you guys can see. So this can be in Pascal also. So this can be in Pascal. Okay. Now there are other equations that represents this graph also. Okay. So the most common one probably you guys have seen is stress is equal to K epsilon N. Okay. So this is a simplified version of what we have that I've written down here, where K is also a coefficient. Now, question now for you guys. Remember earlier when we were to make the material, the first question we were asked, right, is what material? The next question that was highlighted is hardness. Okay. Now, plastic region is where manufacturing operate. Okay. If you deform your material in the elastic region, your customer will take the material and throw it back at you. I want you to deform to a different shape, and you give me the same shape back when I gave you, and I still have to pay you money, right? So we are operating in the what? In the plastic region, right? In manufacturing, we only operate in the plastic region. If you do structure analysis, you operate in the elastic region. You don't want your structure to deform permanently. So the question we are asked is, the first question we ask is what material, and then the next one, and this is still very common, is the hardness. Question for you guys. This is the plastic region of how the material behaves. When we ask what material, where in this stress strain curve do we see it that we're asking? Anyone? What material? Can anyone answer me? So we ask what material. What can you tell me from this graph about what material? Anyone? In the elastic region, it's easy, right? When I ask what material, you're referring to this in the elastic region, right? So this is the elastic region. So when you ask what material, you are trying to figure out this slope. Is it material 1 or Young's modulus? Is it Young's modulus 1? Is it Young's modulus 2? Or is it Young's modulus 3? So this is what material, right? Still useful information. And then the next thing we ask is what? What is the hardness? Now, where is the hardness in this diagram? Anyone? Point 1, point 2, or point 3?